Welcome to Maths with EJD. I have been taking a series of classes on matrices, and in this video, our focus shifts to row echelon form reduction of matrices. So you can call the row echelon form REF. Okay. First of all, we'll be looking at the definition of the row echelon form, and then we'll see how we get the row echelon form by doing some elementary row operations. And then we'll also look at the reduced row echelon form, which is a more refined form, which is an advanced, like when you build on the row echelon form, you can arrive at the reduced row echelon form. It is actually the final stage of the elementary row operations we are going to learn about. And then this will lead us to the idea of row and column spaces. And then from that, we talk about the rank of a matrix. Then we'll talk about the rank-nullity theorem. And lastly, we'll talk about rank and invertibility. Okay, and probably take some exercise if possible. Okay, so we go to the first part, defining the row echelon form REF. As you can see, the row echelon form REF of a matrix is a special form into which a matrix can be transformed through a series of elementary row operations. So you need to carry out some elementary row operations. Of course, we're going to talk about that next. You need to carry out a series of elementary row operations to get a matrix into the row echelon form. Okay, now what's the row echelon form? In the row echelon form, the matrix has a triangular structure. It has a triangular structure where we have two conditions. All zeros, if any, are at the bottom. So if there are 0 rows, those 0 rows must be at the bottom of the matrix. They have to be at the bottom of the matrix. If there are 2 0 rows, they have to be the last 2 rows, depending on the, here you can even have a 100 by 100 matrix. So in echelon form, so all the 0 rows are at the base of the matrix. They are at the bottom of the matrix. That's one. And the second condition is that the leading entry, which is the first non-zero entry in each row, is to the right of the leading entry in the row above it. So usually the elements in row 1, column 1 would be a leading entry. That one is normal. It's very normal to have the element right there to be a leading entry. Okay, so and that's for row 1. So for row 2, the second condition is saying that any other leading entry you're going to have should be to the right of the one at the top, right? So it means that, and since the leading entry is the first non-zero entry, so it means that automatically whatever is before it has to be 0, So mind you, all this, if there's a 0 row, it will be this last row. So all this will be 0. Then because this leading entry has got to be non-zero, then this value also has got to be 0. So you can see that all elements, so the idea here is that all elements below the main or principal diagonal have to be 0, they have to be 0. Of course, because you have a 0 row, of course, this one is also included in this case. All right. So that helps us. So we know the possible leading entries will be A11, A22, A33, like that. And based on this also, we have this possibility. So this matrix B is a very good example of a matrix in echelon form. Why? Because we have of course here we don't have a 0 row. So since there's no 0 row, we don't have to worry about it being at the base. So because if you look at the condition, it says all zeros, if any, are at the bottom. So there's no 0 row here, so no problem. But it's still in echelon form because we have 3 as a leading entry, we have -2 as a leading entry, we have 1 as a leading entry. And you see that each one is one column right of the leading entry at the top. So this is the leading entry. So normally you cannot have another leading entry below. It has to be something that shifts, and then this one also shifts to the right. So two conditions, all zero rows, if any, at the bottom. We don't have zero row here, so no problem. Then the next condition is that the leading entry, every leading entry is to the right of the leading entry on the row above it. So those two conditions have been met. So pretty much it means that all the elements below the principal diagonal, all these three elements have got to be zero, and that has been met. So that means B is a very good example of a matrix in row echelon form. All right, we go to the next one, which is elementary row operations. Just like we've seen already, we cannot get elementary row, we cannot get the echelon form without carrying out elementary row operations. So that's why we have to talk about elementary row operations next. So elementary row operations, right, are the three basic operations. Elementary row operations are the three basic operations that can be performed on the rows of a matrix without changing its row space. Though as you carry out the operations, the values, the elements of the matrix may be changing in value and everything, but the structure of the matrix is not changing. The row space is not changing. In case you're wondering what row space means, we'll talk about that in the next slide. But first, let's deal with these three basic operations. The three elementary row operations are this. You have the scaling. Scaling means you're multiplying a row by a non-zero scalar. It can be a whole number. It can be an integer. It can be any kind of number. It can be a fraction, anything. So you can, as far as you're multiplying a whole row through by a particular number, that is what you can call scaling. The next thing is that you can actually swap two rows. So you can make row 3, you can swap row 1 and row 15 if you, depending on the matrix you have. If you have a 4x4 matrix, you can swap any row with any row. That's basically what that idea is. So, and swapping that row will not change the structure of the matrix. The fundamental structure of the matrix will not be affected by elementary row operation. And then the last operation in the triad is adding or subtracting a multiple of one row from another. So you can multiply a row by a particular number, and then multiply another row by another number, and then add the two together or subtract them, and you still preserve the structure of your matrix. Okay, so to give an example of all these three steps, that's why I have this matrix with row 2, with 2 rows and 2 columns. So you have 3, 2, and 1, 9. Before I forget, we have elementary row operations, right? In the same way, we can also have elementary column operations. So it means your scaling in that case will be multiplying a column by a non-zero scalar. Then your swapping will be about swapping 2 columns. Then so you can add or subtract a multiple of one column from another, right? So you can multiply a column by a number and add it to another one or something like that. So in the case of elementary column operation, it will just be the same thing you're doing with reduced column, like that. So, and in the same way, it's also the matrices still remain preserved fundamentally. Okay, so let's look at this example: a 2x2 matrix with row 1, 3, 2, row 2, 1, 9. So the first thing I'm doing here is to scale each of the rows. So by multiplying the first row by 4, it's more like I am increasing it. I am stretching it out. By multiplying by 1/3, it's like I'm compressing it, so to speak. That kind of thing you do with sound, right? So you have 4R1. 4R1 means that the new R1 for the new matrix is the new R1 for the new matrix you are going to get is obtained by multiplying the old R1, the R1 of the old matrix, by 4. So that means 4 times 3, 12. 4 times 2, 8. Then for the row 2 now, the new row 2 is 1/3 of the old row 2. So the old row 2 is 9. So 1/3 times 1, that's 1/3. 1/3 times 9, that is 3. So that way, though now you have a new matrix, it's looking totally different from where you're coming from. But then fundamentally, because you have carried out elementary row operation on it, it still has the same structure fundamentally with the matrix you started with. And of course, that is scaling. What if we choose to swap the rows because we can also swap, right? So now that this has been done, so this is your new row 1 and this is your new row 2. But then we have another matrix that is coming. And how is that obtained? The new row 1 of this new matrix is actually the old row 2. So that's the swapping we're talking about. So row 1 in the new one is the row 2 of the old one. And that is why the row 2, 1, 3, 1, 3, 1, 3, 3 will come to row 1 here. And then the row 2 of the new matrix is actually the row 1 of the old one, 12, 8. That's why you see 12, 8 coming here. So now that's another change to the matrix, but then it has not changed the fundamental structure because we have done something legitimate. We have done one of the 3 basic operations. So the last thing is about adding or subtracting a multiple of one row from another. So look at so now that I've done this, I have row 1, the new row 1, and the new row 2 for what we have just finished. But then we are going to another place. So this matrix now becomes old, and then we go to the new one. And how am I going to get the new matrix? So the new row 1 for this matrix is going to be 9 times the old row 1 plus the corresponding element in row 2. Now, let's see that. So the new row 1 here is, so like this element 1, 1. So what I'm doing is I'm multiplying 9 by 1 over 3. 1 over 3 of 9 is 3. Then that 3 plus 12, that's why we have this 15. Then for the second element, 1, 2, right? So you multiply 3, the element here, by 9, that's 27. And then you add to 8 because we are talking about the new row 1 being 9 times old R1 plus old R2. So 9 times 3, 27 plus 8, that gives you 35. And then, of course, here, I'm not touching row 2. I've not done anything to that. So I just say the new row 2 is the same as the old row 2. So that's why this is here. So you can see this matrix now totally looks different from where we are coming from. But in structure and row space, it's still the same matrix. And the reason why we do elementary row operation is to simplify matrices for things, to get things like inverse or to solve a system of equations as we are going to solve in future videos. Okay, so I go to the next one where I now talk about reduced row echelon form. Don't forget, I've been talking about the row echelon form, which we obtain by elementary row operations. But then we have an advanced stage of this process. That's the final stage. So the reduced row echelon form is the final stage of the row reduction process. Okay, it's the final stage. It's like with RREF, you have the matrix even more refined to do probably a better job than the than the row echelon form. You're going to see all of that in a jiffy. So now the 2 conditions for the reduced echelon for the row echelon form, you remember, number 1, if there are 0 rows, they should be at the base, they should be at the bottom of the matrix. That's number 1. Number 2, the leading entries, which are the non-zero entries, should actually be to the right of the leading entry above them. Okay, so basically we are saying that all the elements below the main diagonal should be 0. But then we are not specific about the value of those leading entries. But in the reduced row echelon form, right, we have more rules that now those leading entry in each row that we talked about before, we're not in the row echelon form, we're not particular about their value. But in the reduced row echelon form, the value should actually be 1, So your leading entries should actually have a value of 1. Then apart from that, each leading entry now should be the only non-zero element entry in its column. Each leading entry 1 is the only non-zero entry in its column. So, like if you look at the example I gave you the other time in the previous case, right? We don't care as far as if something like this, we have 3, 2, 1, 0, 4, minus 1, and then we have 0, 0, 2. This is already in row echelon form because every element below the principal diagonal is 0. So this is already in the row echelon form, which is okay. So, but in addition, if you are taking it to RREF, that the reduced row echelon form, then this 3 has got to be 1. This 4 has to be 1 also. These 2 will also have to be 1. And then in addition to that, once you have 1 somewhere, like if once you have 1 here, everything below it should be 0. Once you have 1 here, whatever is below or above it should be 0 also. Once you have 1 here, everything above it should be 0. So that is the additional thing, that each leading one is the only non-zero entry in its column. Okay, so to drive that home, let's take this simple example. We have a 3x3 matrix with row 1 as 1, 2, 3, row 2 as 4, 5, 6, row 3 as 7, 8, 9. And of course, whether you're looking for the row echelon form or the reduced row echelon form, you are still going to get that by the normal elementary row operations. Okay. So how am I going to do this? My intention is that at the end of the day, these elements should be 0, first of all, and all these elements, the leading entries, should be 1 or 0. Of course, if all the rows are zeros, then of course this one will be 0 too. But if they are not 0, then this one should also be 1. Then in addition to that, if this one is not 1, then if this one is 1, right? So all these elements above and below should also be 0. Okay, this one already 0, right? Then whatever is above them should also be 0. That's the idea of reduced echelon form. Maybe it may not be so clear right now, but let's understand this. First of all, let's focus on getting these guys to be 0. And for me, of course, you can do it in various ways, but for me, I find it easy to make everything 1. Everything anytime I need to subtract, I just want to make everything 1. You're going to see how I make things 1. So for easy subtraction, so I don't have to worry my head about too many things. So the first thing is, interestingly, the first entry here is already 1. So we have 1 preserved, no stress. So we don't have to touch that. That is why my new row 1 is the same as my old row 1. 1, 2, 3, 1, 2, 3. Nothing has changed. But because this 4 and 7 have to become 0, so what do? I divide through the row 2 by 4. So I say row 2, the new row 2 will now be 1 over 4 of the old row 2. And that is 4 divided by 4, 1. 5 divided by 4, 5 over 4. 6 divided by 4, 6 over 4, or 3 over 2. But I leave it as this so that I don't have to rack my head over that. Okay. Then, of course, this also has to go to 0. So, and for me, since this is already 1, it's easy to subtract 1 from 1. That's why I'm doing this. So because this is 7 here, I multiply the old row by 1 over 7, or multiplying by 1 over 7 means dividing by 7, basically. So if you say 1 over 7 times 1 times 7, or 7 divided by 7, that's why you have this 1. 8 divided by 7, 8 over 7. 9 divided by 7, 9 over 7. So I have that. So the transformation has begun. So the next thing is, now that all these ones are 1, it's now easy to get them to be 0. All I just need to do is this. So row 1 is settled because the leading entry is 1 already, so I don't have to worry. So, but for row 2 now, I need 0 here, I need 0 here. And for me to get 0 in those places, what do? I say that my new row 2 is going to be my old row 2, this, minus my old row 1, because I know 1 minus 1 will give me 0. So 1 minus 1 here is 0. Then 5 over 4 minus 2. How do we do that? If you remember, 5 over 4 minus 2 over 1. The LCM is 4. 4 in 4 is 1 times 5, 5. Minus 1 in 4, 4 times 2, 8. And then finally, that gives you minus 3 over 4. That is how I got this minus 3 over 4 here. Now, if you do the same for 6 over 4 minus 3, another fast thing you can do is, you have 6 over 4 minus 3. To make it easy, if you multiply 3 by 4, you get 12. So this can also be 12 over 4. 3 is also the same thing as 12 over 4. And how do you get the 12? Multiply 3 by 4. That's 12. So this way, you can easily say, 6 minus 12 is minus 6 over 4. That's how this came about. That's how that minus 6 over 4 came about. Then I do the same thing. My new row 3 is going to be my old row 3 minus row 1 again. So I say 1 minus 1. That is 0 here. Then I say 8 over 7 minus 2. Just if you use the fast method I've taught you, 2 in terms of 7 will be 14 over 7. So 8 minus 14, that is minus 6 over 7. Then 9 over 7 minus 3, that's like 9 over 7 minus 21 over 7, because 3 times 7 is 21. So 9 over 7 minus 21 over 7, that will be minus 12 over 7 here. So with that settled, we have a new matrix. We have this new matrix here. Now, we have started achieving our purpose. We have already got this one to be 0, 0. Of course, this one also has to be 0. Now, for this to be 0 now, since you have taken care of all these zeros, so your focus is going to be on this new leading entry. So you can forget about the top. Of course, you just keep repeating that. So this is going to be your new lead entry. And just like I told you, it is always sweet to make these things 1. It's very sweet to make these things 1. So from here now, so I have my new row 1 in this next matrix is still going to be the old one, because that one is settled already. It's taken care of. So, but because this is now going to be the new lead entry, right? So how do I get this one to be 1? It is minus 3 over 4. So all I just need to do is to multiply it by its multiplicative inverse. The multiplicative inverse of a number is the number by which you multiply it, and you get 1. Okay? So minus 3 over 4, I know that if I multiply by minus 4 over 3, I will get 1. So that's why my new row 2 is minus 4 over 3 row 2. So that I know minus 4 over 3 times 0, that will be normal 0. Then minus 4 over 3 times minus 3 over 4, minus 4 over 3 times minus 3 over 4. This is what we had, right? Just turn it over, just invert it. That's why this, so for minus 3 over 4, the multiplicative inverse is minus 4 over 3. So 3 cancels 3, 4 cancels 4, minus and minus is plus, and the answer is 1. So that's why I have 1 here. It's very good to have 1 for this leading entry. So, and because of course you're multiplying through by minus 4 over 3, so minus 4 over 3 times minus 6 over 4, 4 cancels 4, minus and minus is plus, 6 divided by 3 is 2. That's why this one is 2. All right. So, and of course, since I need to get this one to be 0, it's better to also make it 1 so I can easily subtract. So then I just say, so, and that's why I say my new row 3 is going to be minus 6 over 7 times row 3, because I know this is minus 6 over 7. So its multiplicative inverse is minus 7 over 6. All right. So that by the time I multiply minus 6 over 7 by minus 7 over 6, I get 1. Of course, if you multiply by 0, you get your 0 normal. And then minus 7 over 6 times minus 12 over 7. 7 cancels out. 6 over 12 over 6 is 2, because minus and minus is plus. That's why you get this 2. Now, as you are going to see later, the fact that these 2 are repeated should tell you something. It means that this row is easily going to go to 0 by the time we subtract those 2 rows. And that is already telling you something. We are going to learn about rank of a matrix and linear independence later. This is just going to tell you that because all of this is going to be 0, the rank of this matrix will be 1 less than the number of rows it has. Of course, I'm going to drive that home later as we look at the next set of slides. But then we are still on this journey to get the row echelon form and the reduced row echelon form. Okay, so this is what we've had so far. So this is now our new matrix from all the steps we have undertaken. This is our new matrix, and we are still on the journey because we need this to be 0 for it to be in echelon form. But then, we are still going to the reduced row to get it in the row echelon form, right? But we need, we need this to be 0, right? And then we'll still continue the journey until we achieve the purpose of RREF. Okay. All right. So with this matrix now, you can already see a repetition here. So if we subtract, this is going to be 0, as you can see. So row 1 is settled, no problem. So we have row 1. The new row 1 is going to be the old row 1. So 1, 2, 3, we still have that maintained here. And then for row 2 now, since we have achieved 1 here for row 2, so we have this one as people, you can call it pivot or lead entry. That's fine. It's pivot or lead entry because this is the pivot now. We can also, so it looks like row 2 has also come into its rest. Like, row 1 came into its rest way before. So row 2 has also come into its rest. That's come to that place where it has its own lead entry to be 1, which is nice for an RREF like that. So we maintain the old row 1 as the new row 1 and the old row 2 as the new row 2, 0, 1, 2, 0, 1, 2 also. But then for row 3, especially because we need this to be 0, that was the plan from the beginning. So we can now say the new row 3 is the old row 3 minus the old row 2. That means 0 minus 0, 0. 1 minus 1, 0. 2 minus 2, 0. Okay? So with that now, we have the new matrix. And this new matrix, interestingly, fulfills all the conditions. This one now fulfills all the conditions for, it fulfills all the conditions for row echelon form. Why? Because there's a 0 row and it is at the last. And then the lead entries 1 and 1. So this one is a column to the right of the lead entry above it. So this is our row echelon form. So if you're looking for a row echelon form, it's okay to stop here. But of course, I'm using one stone to kill two birds, right? Or how did they say that word? Yeah, I think that's the idea, right? So I have obtained the row echelon form. But of course, you need to pass through the row echelon form to get to the reduced row echelon form. So the journey continues. We are still going to reduced row echelon form. So far, this is what we have to work with. So this is our row echelon form. So if you need it in row echelon form, you can stop here. But to take it to reduced echelon form, of course, we have additional requirements. And the requirement is that if this was not already 1, 1, you have to make them 1, 1. And of course, to make them 1, 1 is just to divide with the whatever. No, if you add 4 here, you just divide through by 4 and it will be 1. If you have 5 here, you divide through by 5 or whatever you have. Or if you have a fraction like 1 over 2, you multiply by 2 over 1 to get it to be 1. Okay, so now we have achieved row echelon form. We are going to reduced row echelon form. And to go there, we know the rules already. The only thing left now is that you have the leading entry here and everything else has to be 0. Now you have this leading entry. You don't have to worry about this for this. So for this leading entry, you're only concerned about things in this corner. All right. So, and it is, oh, okay, yeah, you have to worry. Sorry, that'll be a mistake. So you have this leading entry, everything below it is 0. And for this leading entry now, if it is, as this is the lead entry rather, everything above or below it has got to be 0. So this is already 0, thankfully, but we have to find a way of making this 0. And the only way I see is that this is the pivot or the lead entry that we can refer it to. Although we need this to be 1, but I need to do, in doing this, right, you have to think ahead, like, okay, for me, it's always easy to subtract 1 from 1. So one thing I can do is, since this is already 1 and I'm not going to touch it, I have to leave it the way it is. So I need to make this one 0. And the 2 above that one, I need to make it 0. How do we do that? So, well, I'm going to trade off the first row because I know I can always get back to it. And what I'm going to do is I'm going to make the new row is going to be half of the old row 1. The new row 1 is going to be half of the old row 1, such that I have half times 1, that is half times 2, that is 1, which I really need to subtract from the 1 under it to get 0. Then half times 3, that's 3 over 2. And row 2 is maintained as it is. Row 3 is also maintained as it is. So row 3 is already 0. Row 2, I leave it as 0, 1, 2. So the only thing I've affected is this row 1, which we have been touching since. So now we're only touching it because we want to achieve a purpose of making the element above this second lead entry. We want to make the element above it 0. So now that we have been able to achieve this with this new matrix, then we are still on the journey. So the next thing we have to do is to subtract. So now my row 1, my new row 1 is now going to be this row 1 minus row 2, the old row 1 minus the old row 2. So that means I'm going to have half minus 0, and I put the result here as half. 1 minus 1, then I put the result here as 0, because row 1, the results you're going to, the new row 1 is becoming whatever you get from row 1, old row 1 minus old row 2. That's why this is now 0. Then I say 3 over 2 minus 2. That's 3 over 2 minus 2. 2, if you want to put that over 4, you just multiply this 2 here by 2, that's 4 over 2. So 3 minus 4, that's why you have minus 1 over 2 here. And then every other thing remains 0, 1, 2, 0, 0, 0. Now, this is also a breakthrough for us. We have finally ended up getting this to be 0. All right, that is our plan if you are going to get reduced row echelon form. So with this now, we still have one problem. The problem is that in the reduced row echelon form, all leading entries have got to be 1. So, this was always 1, but we had to change it now because we wanted to achieve 0. So we have achieved our purpose. So we have to get it back to 1, which is pretty easy to do. So now all we have to do is to now say that from this matrix, row 1, row 2, row 3 now. So the purpose now is we need 1 here. And to get 1 there, what is there is half. So to get half to be 1, the multiplicative inverse of half is 2. So 1 over 2 multiplied by 2 over 1 will give you 1. And that is why my new row 1 is going to be 2 times the old row 1. Then the new row 2 is going to be the old row 2. The new row 3 is going to be the old row 3. So our focus is just on the row 1 now, just to get it back to 1. And how do we do it? We just say 2 times half, we get 1. 2 times 0, we get 0. 2 times minus half, we get minus 1. And okay, now check. If you check now, you see that, first of all leading entries are 1. This is 1. This is 1. And wherever we have those leading entries, every element in their column is 0 apart from them. So this is 1 and everything is 0. This is 1, the one above and the one below is 0. And then since this one is a 0 row already, and if there was 1 here, we also have to get this ones to be 0 too. But since there's no 1 here, then this is the destination. We have actually arrived at the destination where we have the reduced row echelon form. And this helps a lot in many things we are going to do in the future. Okay, I know that can be a bit tricky, so you want to go over that portion until, you have to go over it again so you can actually get it very clearly. So that takes us to the idea of row and column spaces. So very straightforward idea. The row space of a matrix consists of all possible linear combinations, all possible linear combinations of its rows. It's a very simple idea. I'm going to explain later. Then the column space now of a matrix consists of all possible linear combinations of its columns. Very simple. And what that means is this. Now, you see, for you to know the row space or the column space of a matrix, it's the best thing to do is to first of all get it into the reduced row echelon form, into the RREF. So based on that, you can now determine the row space and the column space. So from the matrix we had, that matrix was 1, 2, 3, 4, 5, 6, 7, 8, 9. And it led us to this reduced row echelon form, right? So from that previous reduced row echelon form, we can say that this matrix now, of course, in the reduced row echelon form, the row space is the combination of all the possible rows. So these are the possible rows: 1, 0, minus 1. That's why you have this. Then 0, 1, 2. That's why you have this. So that is the row space of that matrix. Then the column space is also the collection of all the possible columns, And now here, we only count the columns where we have a lead entry. So we have a lead entry here. So that's a possible column. We have another lead entry here. That's a possible column. Now, the lead entry that should have been here would be this. Should have been where this 1, where this 0 is. But since it doesn't exist, we do not count that row. That column as part of the column space. So these are the only two columns, that qualify to be in the column space because they have lead entries. The third column does not have a lead entry, so it does not exist. We don't care about it. So that's why our column space is simply 1, 0, 0 and 0, 1, 0. And then we are done with row space and column space. Easy. Okay, so we go ahead to talk about the rank of a matrix. Now, the rank of a matrix also relates with the reduced row echelon form. So if you want to know the rank of a matrix, the first thing you have to do is to get the matrix into the RREF, the reduced row echelon form, which I've just explained. That was a lengthy explanation, by the way. So the rank of a matrix is the maximum number of linearly independent rows or columns in the matrix. Now, this is of course, I think I've talked about the idea of linear independence before, but I'm going to explain it further by the time we are done with this slide. So the rank of a matrix can be considered as the dimension of row space, or equivalently the column space of the matrix. Now, if you go back to the idea of row space and column space we did before, you remember we had just 2 rows in the row space, and we had 2 columns in the column space. They are usually the same. The number of row space is usually the number of column space when you get to the reduced row echelon form. So as a result of this, since the number of row space, the dimension of the row space was 2, then automatically the rank will be 2 also. All right. So the rank of a matrix can be considered as a dimension of row space, or equivalently the column space of the matrix. So for the matrix A, 1, 2, 3, 4, 5, 6, 7, 8, 9, with this reduced row echelon form 1, 0, -1, 0, 1, 2, 0, 0, 0, the rank of matrix A, you can say the rank of matrix A is 2. Why? Because you have two rows in the row space and you have 2 columns in the column space. That's why the rank is 2. And of course, another way to look at the rank is, now you have this one, you have this row, and then the third row is all 0. So the number of rows you end up having in your RREF tells you the rank of the matrix. So the rank is 2. So since there are 2 non-zero rows in the RREF, so these are the 2 non-zero rows, then the rank of the matrix is 2. So if you are told to find the rank of a matrix, the first thing you want to do is to take the matrix into the reduced row echelon form and count the number of rows that are non-zeros. Then that will give you the rank of the matrix. So in this case, it is 2. In case there are non-zero rows, it means that you have 3 zeros. So in that case, we say that the matrix has full rank. It means that the number of rank is equal to the number of columns of the matrix. All right. So again, the third column of the RREF does not have a leading one. So because this third column does not have a leading one, so it can be expressed as a linear combination. It can be expressed as a linear combination of the first 2 columns. So that means that this column, okay, the third column rather. So this third column, right, is a linear combination. The third column of the RREF does not have a leading one. So this one doesn't have a leading one, like I said before. So it can be expressed as a linear combination of the first 2 columns. So this -1, 2 can be expressed as a combination of these 2. And I think that makes a lot of sense, right? Let me attempt to do that so you can get the gist. So you can see that -1, 2, 0, which is the third column, you can actually express it as, you can say it is, how do I get more space? You can express it as minus the first column, that's 1, 0, 0, you can express it as minus 1, 0, 0, right? Plus 2, 0, 1, 0. If you understand that. So -1, that's what you have here. Plus 2, that's what you have here. So it's more like you have this to be -1, 0, 0 plus -1, 0, 0 plus 0, 2, 0. If you add it all up, -1 and 0, that's -1. 0 plus 2, that's 2. 0 plus 0 is 0. So you see that this last column now, because it does not have a leading entry, is a linear combination of the first 2. That is the idea there. And in that case, that means, so this shows dependency between the rows. So it means that the rows are dependent on themselves. And that is the idea of linearly independent we talked about before. But here, so for this particular rows, for this matrix, the rows are linearly dependent. And once they are linearly dependent, it has something to do with whether it has an inverse or not. So let's look at that as we talk about the rank-nullity theorem. So all these things are interwoven still. So talking about the rank-nullity theorem now. So the rank-nullity theorem states that for any matrix A, the sum of its rank, of course, the rank, we already know the rank is the dimension of its row space. So after you have taken it to the reduced row echelon form, the number of non-zero rows remaining is the dimension of the row space. For this matrix, it's actually 2. And its nullity. So when we talk about nullity now, the nullity is the dimension of its null space. And the dimension of the null space is the number of the 0 rows. That's the nullity. And so the rank-nullity theorem states that for any matrix A, the sum of its rank and the sum of its nullity rather equals the number of columns in A. So for this matrix A now, for this matrix A, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, with the reduced row echelon form of 1, 0, minus 1, 0, 1 to 0, 0, 0. You remember the process we went through to get this. So at the end of the day, the dimension of its row space is 2, because at the end of the day, we have 2 non-zero rows, and the nullity is 1 because we have 1 0 row. So 2 non-zero rows means rank 2. 1 0 row means nullity 1. So what the rank-nullity theorem is saying is very simple, that if the rank is 2 and the nullity is 1, if you add the rank with the nullity, you get the number of columns. So number of columns is equal to rank plus nullity, 2 plus 1, and that is 3. Of course, we know the matrix has 3 columns and 3 rows. So it looks very simple and straightforward, but I mean, just to get the concept. Of course, we are only using 3 by 3 matrix here because you can get to maybe when you get to a coding environment. Now, matrices are very important if you are a programmer, for instance, a software developer, because most of the times you have to represent whatever you're doing as a matrix for easy handling. So things are better handled as when you put them in matrix form. Okay, so we go ahead to talk about the idea of rank and invertibility. So you can see inverse has been following us since we started from way back, right? So because it's very important. So the rank of a square matrix is equal to its order if and only if A is invertible. Now, this is related to where we're coming from, right? So of course, the order of a matrix, the order of a square matrix, order of square matrix, the order is simply the number of rows, number of rows or columns. That is the order of a matrix. Since the square, the number of rows is equal to the number of columns. So either number of row or number of column, that is the order of a square matrix. So this one is saying that the rank of a square matrix A is equal to its order if and only if A is invertible. That means if you can find the inverse of a matrix, it means that the rank of that matrix is equal to the number of rows or the number of columns of that matrix. So if you have a 3 by 3 matrix and it has an inverse, you can find the inverse. The inverse is not 0. Then it means that the rank of the square matrix is equal to the number of rows. So it means that the rank of the square of that 3 by 3 matrix is 3 because you are able to find its inverse. In other words, if a square matrix has full rank is the rank that is equal to the order, and the order is the number of columns. So if you have 3 rows, 3 columns, and the rank is 3, that means the rank is equal to its order. And in that case, you say it has full rank. Full rank means at the end of the day, but if it's a 5 by 5 matrix, and you do you would take it to the reduced row echelon form. At the end of the day, the rank is 3. That means the rank is 5. If it's 5 by 5, right? At the end of the day, all the rows are non-zero. So that means that it has full rank. So the number of rows and columns is 5. And then the number of non-zero rows is also 5. That means the rank is equal to the order. So if a square matrix has full rank, where rank is equal to the order, it means its rows and columns are linearly dependent. Is it linearly dependent? It should be linearly independent. Sorry, it should be linearly independent because it's full rank, right? The other time when it's not full rank, it was linearly dependent. So this should be linearly independent. And because it is linearly independent, it is possible to find a unique solution for a system of linear equations represented by the matrix. We're going to be solving systems of linear equations along the line. That is why all this is very important. So, and just like I told you, no determinant, no inverse. No inverse, no solution to system of equations coming from that matrix. So you need linearly independent rows or columns for you to be able to find all the exact solutions of a system of equations. That's why we are talking about all this. In essence, a square matrix is only invertible if it has full rank. So if it has full rank, then it is invertible. and once that's an inverse, then you can use it to use it to solve system of simultaneous equations or system of linear equations or what we call simultaneous equations. So in essence, the square matrix is only invertible if it has full rank. That is, the rank is equal to its number of columns. So if the rank is equal to the number of columns, you say the matrix has full rank. And because it has full rank, you can find its inverse. And because it has full rank, you can say the columns or rows are linearly independent, not dependent, linearly independent. If the rank is less than the number of columns, then you can say that the rank of that matrix is not full. It doesn't have full rank in that case. Also, all the rows of a square matrix, are linearly independent if the matrix has full rank. That's what I've just said. And they are linearly dependent otherwise. So I can make a simple law here, of the fly, on the fly, that if rank is less than order, and of course you already know that order is the number of rows or columns. If rank is less than order, so it means that rows are linearly dependent. Okay, the rows will be linearly dependent. But if rank is equal to order, so you have linearly independent. And if they are linearly independent, you can find the inverse. And if you can find the inverse, then you can get unique solution to the system of equations arising from that matrix. Very important. Of course, you cannot have rank greater than order, because you cannot have any rank greater than the number of columns or rows a matrix has. So you can only have rank less than the order or rank equal to the order. So rank less than order, not full rank. Rank equal to order, that's full rank. Full rank means linearly independent. Linearly independent means you can find the inverse. Then you can solve the system of equations that will be arising from that kind of matrix. So this has been a long one, I want to believe, and you have some exercise to play with. And just like, teachers give you simple examples, 1 + 1 = 2, and then they give you x - 2y. That's how we do it. So enjoy. So this is your exercise. Determine the ranks and nullities of the following and state if their rows are linearly independent or dependent. Of course, to find the ranks and nullities, all you just have to do first of all is to take each matrix to the reduced row echelon form. And once you get there, if there are 0 rows, the number of 0 rows you have will be your nullities, and the number of non-zero rows you have will be your ranks. Okay. And then if there are 0 rows, that means the rows of the matrix are linearly dependent. But if there are no 0 rows, meaning that the rank is equal to the number of columns, then you can say that the rows of the matrix are linearly independent. Okay, so that is the idea. Thank you so much for listening to this. See you in the next video. I think in the next video, I should be talking about how to find the inverse of a matrix using the row echelon form or something like that. I believe that should be what we'll be talking about next. So see you then. Thank you for listening. If you have any suggestions on what I can do to improve, or you have some questions that you'd like me to solve along the line, let me know. See you.